this is Mr. Collier, and today we are looking at some equations of planes. And here we have a picture of a plane which extends in all directions. It's a flat surface that extends in all directions. Notice we can describe a plane with, if we have two direction vectors, then it creates a plane, right? There's only one plane that contains these two non-parallel vectors, right? But the C and D, they could be on a different level, like down here. So there's an infinite number of planes, but they're all parallel to each other. So as soon as you talk about one point, like point A, then only one point goes through point A and through vectors C and D. So a point and two direction vectors describe a plane. So the vector equation of a plane can be given by this equation, where A is a point on the plane, any point. B and C are two vectors parallel to the plane. Mu and lambda are scalar multiples, or scalars, and R, of course, is the vector xyz. It's just short for xyz. Okay, the most important thing about the vector planes is the normal, right? The normal is perpendicular to the plane, so it's perpendicular to every vector on the plane. So we can describe equations of the plane using normals as well. All right. Basically, if you take the normal and you dot product with any point on the line, it should be always the same. So any point in the line, dot product with the normal should be equal to that particular point A. It's the same A, dot product with N. So if you do that, if you do this dot product, you get, R dot N would give you AX plus B, Y plus C. Like N is just A, B, C. Okay? And if you do A dot N, you get some sort of constant D. So this is basically the same equation, just written two different ways. Alright? Like for example, if the normal to the plane is 1 to negative 1, then we can do the dot product with xyz, and we get 1x plus 2y minus z equals 4. So these are two different ways of writing the same thing, right? Okay. So anyway, these are the three different versions of the equation. We're going to use those later. First one, convert vector equation to Cartesian form. So again, it's all about the normal. And the normal is going to be perpendicular to these two direction vectors. To get a vector perpendicular, you got to do the cross product. Okay, so let's do the cross product of these. Okay, we're going to get 1 minus 1. We're going to get, that's that. Oops, I wrote down the wrong thing here. That's a 0 right there. Okay, sorry. So 1 times 1, we get a 1 here. And then over here, we're going to get a negative 1, negative 1. So it's going to be a positive 1. And then we're going to get a negative 3. Okay, so this is a normal to the plane. So then to get the equation, we can do xyz dot 1, 1, negative 3 equals 1, 0, 1 dot 1, 1, negative 3. Okay, and this gives us x plus y minus 3z equals 1 minus 3, so that is x plus y minus 3z equals negative 2. This is Cartesian form. You can see the normal just looking at the coefficients, 1, 1, negative 3. And 2 we got by doing the dot product of the normal with a point on the line. Okay, so that's how you do that. Moving on to the next one, find the equation of the plane containing these 3 points. So if they're not collinear, then these form a plane. And to do that, we need two directions, and then we get the normal to the plane, right? So we need probably, AB and AC. Okay, AB is B minus A, get 3, negative 1, negative 3. And for AC, we do C minus A. We get negative, so we get 1. Oh, I got these backwards, sorry. This is AC, and this is AB is B minus A. We get 1, 4, 0. Okay, so those are two directions, two direction vectors on the plane. We do the cross product to get a normal. So 1, 4, 0, cross 3, negative 1, negative 3. Do that cross product. We get 3. Oh, sorry, negative 12, I mean. We get negative 3, so that's positive 3. Then we get a negative 13. Okay, or you can write it as 12, negative 3, 13, because that's the scalar multiple of that one. Okay, so we use this as the normal. And to get the equation in Cartesian form, actually they did, oh yeah, we can, actually we could write the equation now in vector form just from this information, right? Let's do that first. A point on the plane is this, lambda 3, negative 1, negative 3, plus mu 1, 4, 0. If we want Cartesian form, we need the normal, and we need to do this, r dot 12, negative 3, 13 equals a point on the plane dot with the normal, and we get 12x minus 3y plus 13z equals 12 minus 6 plus 39. So 12x minus 3y plus 13z equals 45 is your answer in Cartesian form.